All right, so we're on our final lesson of the course. I know you're excited. I am. No, I'm going to miss you guys. I hope you've enjoyed the course, and I hope it's helped you improve your Algebra 1 skills. And so we're going to take a look today at solving exponential equations. Just like it sounds, we're going to have an exponential equation, meaning the variable is up in the exponent. That's one of the main reasons they're called an exponential equation. And we're going to see if we can find the solutions that make the exponential equation true. In other words, another way to think about it is we are going to be finding a missing exponent. We're going to be finding what is a value for x that makes something in an equation true. We're going to start off with the method of equating exponents. This occurs when you have an equation, and I'm going to go ahead and warn you, I'm going to make some of these up right off the top of my head here. I do have a few that are pre-made for you, but I'm going to make a few up right off the top of my head. And so there might be some ugly parts of this, just because I'm making some stuff up here. So let's say we have something that looks like this guy right here. And what I mean by equating exponents is we're going to use this method if we can take both sides of this equation and rewrite them to be the same base. Now, the tendency, a lot of times when people run into this problem about equating exponents, they want to look at it and say, oh, just I divide this by 4 and it'll make it 2. That's not what we mean by rewriting both sides. That's actually using a solving technique, which means if you know something's multiplying by 4, you can divide it by 4. But here's the tricky part. What you do to one side, you got to do to the other. That is not going to keep both sides the same, and you're going to end up messing up the 2 over here. So what we're talking about when I say rewriting it so that both sides are the same base is what I literally mean by that, I should say, is to take this 8 and instead of an 8, I'm going to rewrite it with the base 2. Huh? Now, what that means is you need to know that a base is a number that you raise to an exponent. So if I want to raise 2 to something, some number, and get 8, what would that be? 2 to what power gives me 8? That would be 2 to the third power is 8. So notice what I've done. This right here, this 2 to the third, is 8. I did not change the problem by dividing both sides. I literally made 8 just look different. That's what we mean when we say we rewrite something. We make it look different. So what that tells me now is that this 2 to the 4x is equal to all this mess over here. So now what we're going to do on this side over here is we're going to do a little bit of simplifying. Now this goes back to a property of exponents that you should have seen in your pre-algebra classes and probably even practiced a few times in a little bit of algebra 1 stuff, but this is a little bit uglier. You have 2 to the third power and x minus 3. Whenever you have an exponent raised to another exponent, you multiply them. Let me show you just real quick why that happens. If I have 2 squared to the third power, that means I'm doing 2 squared times 2 squared times 2 squared, which is 2 times 2 times 2 times 2 times 2 times 2. How many are there? There is 6 of them, so 2 to the 6th power. That means this is equal to that. In other words, 2 times 3 gives me 6. So I can skip all this junk of explaining how I got that exponent just by knowing that when you have a power or an exponent raised to another one, you get multiplication makes you get the same answer. So that means I can multiply 3 times x minus 3. So 3 times x and 3 times 3, that's 9. And now I have both sides with the same base. Now, that might not mean anything to you still if you're not really paying attention. Let's do something just a little bit easier than that. Let's say I gave you 4 to the x power equals 4 to the third power. What would you tell me x has to be? I hope you're screaming at your computer that x would have to be 3. Because if you have 4 to the x power and it's equal to 4 to the third, that means these two things have to be the same in order for those to be equal. Guys, you can't put anything else right there and make it equal 4 to the third. You would have to plug in 3. So what we do is we use the same concept here, but it's just a little bit uglier. 2 to the 4x equals 2 to the 3x minus 9. That means 4x has to be equal to 3x minus 9. And so then all I have to do is solve this just like I did back in the solving linear equations. Subtract the 3x. It gives me x equals negative 9. So that one ended up not being too bad by the time we got to the bottom. But the key thing here is that I can take this and rewrite it as the same base. And then because they have the same base, they have the same exponent. So let's do that again. Let's say I have, I don't want to use 4 again. Let's say we use 9 to the 2x power equals 81 to the x minus 7 power. Again, just making them up. All right, so here we go. So we got 9 to the 2x. Now, there's actually 2 different ways you could actually approach this particular problem. One is you can look at it and say, okay, 9 to the 2x, I can rewrite 9 to be 3 squared. But then I'm going to have to rewrite 8 with the same base. So it would have to be 3 to the 4th power is 8. You can use your calculator to help you if you can't get that in your head. That's one option. The other option, which is probably the one that most people will notice quicker, I think, if you got 9 to the 2x power, you can rewrite 81 as 9 to the 2nd power, and then the x minus 7. Either way, I'm going to get the same answer when I get done. So what I want you to do from here is see if you can finish it out from here. Make sure you pause the video because I'm obviously going to keep talking. I'm not just going to sit here by myself. So when you finish, hopefully what you noticed is you have this power to a power again, or exponent raised to another exponent. 2 times 2x would be 4x. 4 times x minus 7 is going to be 4x minus 28. And then so what I do there is this base is equal to this base. That means 4x would have to also be equal to 4x minus 28. This one is going to give us an interesting answer here, because if I subtract 4x, I'm going to get 0 equals negative 28. That is not true. That means there is no solution that would make this exponential equation true. Then if I come over here to this one, I do the same concept here. I leave the 9 to the 2x, but over here I do 2 times x minus 7, the exponent raised to another exponent. You get 2x minus 14, and then that means 2x equals 2x minus 14. But again, you're going to notice the same thing happen. You're going to get 0 equals negative 14, which still tells you no solution. So it doesn't matter what base you get the equation to, as long as you can get both sides to be the same base. All right, so what if you can't? Well, this is actually the one that's going to be probably more real world applicable for you, because you can do this when you're thinking about a bank account. So what I'm going to look at first is just we're going to start a problem about a bank account, and then I'll come back to what you do in just a second. So what I mean by that is, let's say we have a bank account, and we deposit $1,000 when we graduate from high school or college, and that's because Mr. Harrison told us to when we were doing this Algebra 1 overview, and he told us to save our money. We find a bank account that is 1.5%. That's not a high interest rate, but that's about normal for an online bank account especially. That means my function, let's practice writing a function again, 1,000 is my beginning amount, 1 plus 0.015. We move the decimal place, remember, 2 places. Raised to the t power. And you could also add that 1.015 together there. but this function describes what's happening in my bank account. Now, earlier in the chapter, what we did is we said, okay, if I know how much I plug into my bank account, like $1,000, and I know that I got 1.5% interest, so 0.015 there, I can raise that to any power I want to. Let's say 5 years. I do 5 years, I'm going to only make $77.28. So $1,077.28. Okay, so that's for 7 years. Let me write that down over here. Now again, that's not much, but again, remember what we talked about with this. That's only one deposit, and you only left the money in the bank. You didn't really do anything for the money. Remember, I showed you some really cool things with Dave Ramsey's website about how if you start depositing more money into a bank account, you could start seeing some really big amounts because you're saving money and adding more every single month. But what happens is, typically, most of us have some type of goal in mind. Specifically, let's say in this particular example, my goal is to get my bank account up to $1,500. Now, obviously, if you're making more deposits, that's a whole lot easier. But if you only make one deposit, I want to get $1,500. How many years is it going to take me? Notice 7 years took me this to get there. That's going to mean it's going to probably take me a little while. But here's what we mean mathematically in an equation. We're actually plugging 1,500 in for y, not for x, not for the t. We're going to find the t. So that's a missing exponent. Now the first thing, I'm going to treat it just like I would a normal equation. I'm going to divide that 1,000 over to this side, and I get 1.015 raised to the t, and 1,500 divided by 1,000 is going to be 1.5. So I want to know when this equals this. But I can't get that to be the same exponent, or same base, on both sides. Because I don't know how to write 1.5 as a base, or 1.015 even worse, right? So there is something that I'm going to show you here, and we're not going to get into the huge details behind it, but it's basically the opposite of exponential. So the opposite of exponential is finding what we call a logarithm. I know it's a weird word, but a logarithm is when you find the missing exponent for a number. Basically, a logarithm is exactly what it sounds like. You actually write the word log, and then you put the base over here. You have 1.015. That's the base number. Inside the logarithm, you put the number you're trying to find, the answer, so to speak. But then the answer to this logarithm is going to actually be the value for t. So it's something I always tell people when I'm doing my Algebra 1 classes and things. It's this base raised to this exponent equals this number. That's the definition of a logarithm. So the base raised to the exponent t equals the 1.5. But here's the cool thing. You've got Desmos. And so all I have to do is go to Desmos. And so I'm going to go to Desmos and I'm going to say, all right, I'm going to do the logarithm. Now you probably can type it in, but I also want to show you it's underneath this little button for functions, because underneath here you have a lot of things that you'll be able to use in your future math classes. I believe it's under miscellaneous, if I remember right. Yep. Down here you see log and log A. I'm going to choose log A because I want to actually type in 0.015. The other one is actually a special logarithm that has a base of 10. So this is logarithm of 1.5, but the base number raised to this exponent should give me 1.5. 1.015 raised to the 27th power equals 1.5. That's what the definition of a logarithm says. And what it says in the case of this particular example that I'm giving you is it says that the time that it's going to take me to get to that is going to be about 27.23 years. If I'm looking at an interest earning account that only adds interest once a year, then that means I'm going to have to actually go to 28 years before I have $1,500. That's going to be a long time to wait. This is why I told you it's very important to make sure that you actually go through and make more deposits. So this is the real world application of that. You can also do this taking a logarithm on each side like you look at here, like I showed you just a second ago. When you look at it taking a logarithm, what you can look at is also things that are just nice other types of logarithms and not just for a bank account. So what I mean by that, sorry, words getting stuttered there. 4 raised to the 2x equals 10, and you want to find the answer for this x right here. Remember, this base raised to this exponent equals 10, right? So you do log base 4 of 10 equals 2x, because the definition of a logarithm says this base raised to this exponent equals this number. That's what I got right here, guys. This base 4 raised to this exponent 2x equals this number 10, because that is what is right here above it. So then I just take out my handy dandy calculator again. I am going to have one extra little step here. I am going to have to divide my answer by 2 because it's going to give me x that way. You're going to notice these give you a lot of decimal answers because you're finding some weird exponents here. Let me see if it lets me do logarithm and do and I don't think it's going to let me do that. Get the subscript there. Does it have a subscript anywhere? I don't see one. All right, so we'll go over to the functions and go back to log a there. Sorry, guys. I was just going to see if it'd let me do that. 4 of 10 equals 1.66096. And I'm going to take that whole thing and divide it by 2. So it's 0.830, so that's okay if I round that to 2 decimal places. A lot of times with logarithms, I like to round to 3 decimal places to try to be more exact. So this right here gives me the answer for x. It means if I take 4 and I raise it to the 2 times 0.83 power, I'll get 10. You can double check the answer there by looking at Desmos and saying, okay, 4 raised to the 2 times 0.83 power, and that should be pretty close to 10. That's 9.986. That's pretty close to 10. Obviously, if you're really wanting something to be really precise, you may have to add a few more decimals to this. But that's how you find a missing exponent. It's more appropriate and easier for us, better for us to do that with things like this bank account when we're looking at that bank account there. This bank account example gives us the ability to really apply this concept of finding a missing exponent into something that means something to us. Now, obviously, you'd have to get into a lot higher level of equations and things if you wanted to start analyzing, well, how many deposits do I need to make, extra deposits, because this is just a one-time amount. But it does give you maybe a little bit of help if you're talking about maybe like something like more of a stock environment where you put your initial amount in and you leave it there. You buy a certain amount of stocks and you just leave them there, and you know what happens over time with percentages. You can figure out some stuff like that. Well, let's do that. Let's just do a fun little example of that real quick. We can see another example of that. So let's say we look at a stock environment, and we are looking at depositing a signing bonus from our boss. And so we take $10,000 from our boss immediately, a signing bonus, and that can happen in different jobs. And we deposit that into a bank account or a stock market account that's over time growth funds actually earn between 8 to 12%. And I know that's hard to believe. Sometimes you don't think you're going to get that much. We'll go on the low side though. We'll go say 6% here. What that looks like is 10,000 times 1.06 raised to the t power. Again, we could figure out how much we're going to have if we take out our calculator and we plug it in and we say, okay, I want to figure out how much I'm going to have after a certain number of years. I can just type that in. I can say 10,000 multiplied by 1.06 raised to the, let's say we're going to go 30 years. We're going to leave that. That's going to be $57,434 there. $57,434.91. Okay, that's pretty good. So then let's say we say, okay, well, I don't really need that much from this. I'm looking for a good return. Don't get me wrong. I'm looking for this, though, to be a good vacation on my 10-year anniversary. You know, I plug in 10, see how much I'm going to have. Or maybe I know that my vacation is going to cost $20,000. Now, I know that sounds ridiculous, but $20,000 for a vacation, that'd be pretty fun. That'd give you a really good vacation. So what we do is we plug in 20,000 for Y instead of plugging in a time for 30 years. So we go here and we do just like I said on the other one. We're going to divide by 10,000 to get this base of 1.06 by itself. So we have this base raised to the exponent equal to 20,000 divided by 10,000, which is 2. So we want to know when this base raised to this exponent is going to be equal to this number 2. That's what a logarithm gives me an answer for. Logarithm base 1.06 of 2 equals t. That's what a logarithm does. It says this base raised to this exponent is going to give me this number. So it helps me find an answer for a missing exponent. And so what we're going to do, and this will be our last problem here, we're just going to go to our calculator here and do our logarithm again. Base A right here, remember, on Desmos, 1.06 of 2. It's going to take me 11.895 years, or a little bit really closer to 12 years, especially if your interest is only added once a year. So it's 11.89 approximately, but 12 years if your interest is only added once a year. So can I go on my 10-year anniversary? No. Probably going to have to make some kind of adjustment there to say, okay, I need to maybe invest in something a little bit higher interest if I can find something, or maybe I need to, maybe make some more investments, or I'm going to have to supplement that with some other type of income from somewhere else. So that is the end of our exponential functions, and that's the end of our course, guys. I hope you learned some things. I hope you enjoyed it. Just let me know if you need any help to finish this guy out. Make sure that you realize you're going to be looking at all your module quiz for the exponential functions, and you're going to also be looking at comparing linear, quadratic, and exponential with your final project of a little table that's going to be like some notes for people to look at.